We are going to look at potential energy diagrams, and this is really the path a reaction takes going from reactants over to the products. You will see this on page 5 and 6 of your homework packet. I'm going to flip right away to a metaphor or an analogy for this in something that might seem more familiar. And that is just looking at altitude changes. So here is Denver, about a mile up, 5,000 feet up, we'll say. And you're at a specific household or place there. And you want to get to a specific spot in the resort of Vail, and that's at 8,000 feet. Okay, so you're going from 5,000 to 8,000 feet, except in order to go from Denver to Vail, you have to go through a mountain pass. Okay, so it looks like you have to go all the way up to 10,000 feet, and then you could coast all the way back down. Now in reality, there might be foothills and then some ups and downs and things on the way, but it is a long climb up, and then you can definitely coast at least part of the way right here. So we're going to assume it looks like this. So looking at this, going from Denver to Vail, we have the overall elevation change is going from 5,000 to 8,000. It would be plus 3,000 feet. What's the difference in elevation going from Vail back to Denver? It is minus 3,000 feet. That is the difference in elevation. It really doesn't matter what path you take. The difference between Denver and Vail is plus 3,000, or Vail to Denver would be minus 3,000. Now let's say we take this particular path. How much energy would you have to apply before you could start coasting? You'd have to apply what? Enough to go up to 10,000 feet, and then you could start coasting. So we're going to say that the distance climbed would have to be 5,000 feet, from 5,000 to 10,000 before you could start coasting. In the reverse direction, I can't just coast onto Denver. I have to get up over this hill. I have to climb from 8,000 to 10,000, which would be 2,000 feet, and then I could coast back down right to here. So again, the height of the hill in this direction going left to right would be plus 5,000. The height of the hill going from right to left would be plus 2,000. Notice this height of the hill is going to be path dependent, because if you went a different path that had a higher hill, you'd have to climb higher and descend higher. But going from Denver to Vail and the elevation difference is a state function, because it doesn't matter which path you take, it would always be the difference between 5,000 and 8,000 feet, which would be 3,000 feet right here. Okay, we're going to see some similarities when we look at our potential energy diagrams to this altitude analogy with Denver and Vail. So we're going to bring this thing in over here, and hopefully that'll hold up. I think we're okay. And I'm going to do a reaction where I take HI, and I have two of those molecules. It's an endothermic reaction. I'm going to apply some energy, and it's going to break those things up into H and I, and then the two H's will collect together and the two I's will collect together. So my reactants will be down here, 2HI. My products will be the H2 and the I2, which are separate from each other. So let's take a look at this reaction path diagram. Now I set up an axis here. I'm not too worried about the numbers. It's not really like an actual elevation. I'm mostly concerned with the differences in numbers when we go from one step to another step. So we're going to call this our basis point 0, not that it has zero energy right here, but we'll call that ground zero right here. Okay, and that's where our 2HI is. Now what happens is where we end up is over here. What's the difference? Looks like 5, 10, 15, it's plus 15. So going from HI to the H2 and I2 products, you have to add 15 kcals. What if I started with H2 and I2 and did this in reverse? Then it would be minus 15. I would release 15 kcals. So we think about a lot of reactions going in one direction, but we're going to find reactions sometimes go in two directions or can be reversible. If it takes energy to go from left to right, it's going to release energy going from right to left, and it'll be the same quantity of energy. So delta H stands for the change in heat content. The F stands for forward. It's plus 15 going from the reactants to the products, and it's minus 15 going from the products to the reactions. In the forward direction, it's endothermic. It's absorbing energy from the surroundings. In the reverse direction, it's exothermic. It's releasing energy to the surroundings. Okay, now going from left to right, I have to climb a hill. How much energy do I have to apply to make this reaction go? I have to go from 0 to 25. It's plus 25 kcals. Okay, at this point, I reach the activated complex. It's the point of collision where old bonds are breaking, new bonds are forming, a very unstable spot where the H2 and the I2 are all smushed together in one thing. Kind of like if two cars collide, they come together at one point and then they end up pushing off from each other. So we get up to this activated complex and then we go to a little bit lower energy spot right here, but still higher than what we started with. The EA, or the activation energy, is what that stands for. The energy to trigger that reaction is going to be plus 25 in the forward direction. What if I tried to do the reverse direction? I'm going from higher to lower energy. Can I just coast down the hill? No, you have to apply some energy. In this case, the activation energy in reverse would be plus 10, and that's this amount right here. So, again, we talked about a state function, which means these two are state functions, the difference in delta H, because it's the difference between the starting and ending point. No matter what path you take, it's going to be plus 15 going from left to right, minus 15 going from right to left. But if you have a different path, it could take less energy or it could have a higher activation energy depending on what that path is. When we did heats of reaction in last chapter, we were only concerned with the starting point and ending point. Rates of reaction is all about how long it takes to climb this hill. So the higher the hill, the higher the activation energy, the slower the rate of a reaction will be. I think what you can do now is you can try to look at questions 1, 2, and 3 in the practice here. I'll probably have a supplemental video which you can take a look at and try to make some sense out of that.